Yeah. So make sure the screen is visible to you and I'm audible to you. Good evening, Shiva. How are you? Good evening, Ashira. Good evening, GNV Nizamabad, I think. Good evening, Shravani. How are you guys? So we will wait for 1 minute more. Let the others to be in. Okay. Okay. Good. Screen is visible. Audible. You can also give me the thumbs up. Okay. Very good. So fluid mechanics is the very important chapter. Okay. So try to be focus. Try to solve the numericals. And if you have faced any kind of issue, you will directly say it to me. Okay. Got it? So we are here with atmospheric pressure and gauge pressure. uh, Before that, we have covered the fluid pressure and fluid. What is a fluid? The basic question. Pascal's law we have also discussed. And based on the Pascal's law, the application of Pascal's law is hydraulic machines. And that hydraulic lift is there and hydraulic brakes are there. Then we have seen the variation of pressure with depth in a fluid. And here the fluid is static. Or if you're finding trouble with this word, it is similar to rest. Okay. Now we are going to see the atmospheric pressure and gauge pressure, and then we will move further, and we will also see the variation of pressure when the container is moving with some acceleration. Now, now what is atmospheric pressure? So by the name of it, you can imagine or you can guess that it is a kind of pressure which is exerted by the atmosphere, because in atmosphere we have multiple of gases, like nitrogen, oxygen, carbon dioxide, sulfur dioxide, nitrous oxide and its compound. So lots of gases we have in our atmosphere. So these gases are exerted a pressure on the earth. Okay, because they have mass, so they can exert the pressure. Got it? So this results in the atmospheric pressure. The pressure exerted on Earth's surface by the atmospheric surrounded by it. And why the atmosphere is there? Atmosphere on Earth is because of the gravity of Earth. Okay. Got it? So atmospheric pressure is the pressure which is exerted by the atmospheric gases present in the atmosphere. Okay. Now, so the definition, the another definition, I have told you the simpler one. It is the pressure exerted by the atmospheric gases on Earth's surface, or simply you can say it is the pressure of atmosphere at any point is equal to the weight of column of air of unit cross-sectional area extending from that point to the top of atmosphere. Okay, so it is similar to that. We have the Earth surface and this is the air column of unit cross-sectional area. So there is an air inside it. The pressure exerted by this air on the Earth's surface on this particular area is considered to be the atmospheric pressure. Okay. Now, this situation. So the density is more here, nearer to the Earth's surface, because here the value of gravity is high. And as you move up, we have seen this concept in the gravitation. When you move up, the gravitational acceleration or the value of gravity will decrease. Okay. Just a second. Huh? Okay. So the nearer is the air, the denser is the air because it attracts towards the Earth's surface. As you move away, the number of molecules of gases will reduce because there is no much gravity to hold there. Okay. So if you talk about this point A, above it, this is the height. So this much weight of air acting as a pressure on at point A. If you reduce this point A, okay, so these are the molecules that contribute the pressure at this altitude. At point B, these are the molecules. These are the molecules. You know? So at sea level, what its value? So we measure the number of the weight of the molecule. Okay, weight of the molecule from the sea level to the atmosphere, and we will calculate this weight by area so that we have the value of atmospheric pressure. Now, this is a very difficult task to achieve. How we are going to achieve it? It is not feasible to calculate the weight of entire air that is present, complete air, and to weight it and to the calculate it for a particular area. So, how we are going to measure this? How we are going to measure this atmospheric pressure? So, definitely, we are going to use some devices that help us to measuring the atmospheric pressure. And the very first device that we have is the barometer. Okay, you can also say it barometer. So this is the device which was developed by the famous scientist Torricelli. He was the young scholar of Galileo Galilei. You must have heard about Galileo Galilei. So Torricelli was the young scholar of Galileo Galilei. So he has developed a device which is termed as barometer. So it is used to measure the atmospheric pressure. Now, this is the mercury, full of mercury. This container is full of mercury we have. And this column, initially, this column was like this. Okay. And it is closed at both the end. And there are mercury filled inside it. This is mercury. What we have did, we have just tilt this tube and put it inside this liquid. So what will happen when you remove this cap? So mercury will allow to mix in this container. Okay. So it will reduce the weight of the mercury will reduce by this amount because some of the amount was filled in this container. Okay. Now at this particular height, the mercury inside this tube will stop falling down. Why it is so? Because there is no some such air or anything inside this tube because this tube is completely filled with mercury. So there is no existence of air. So this, what we have developed is the vacuum here. Okay. And the weight of the mercury, which is acting downward. Okay. So what is happening? Why this mercury is stop after being covered this height? Why is this stop? Because the air on this container will exerting a pressure, and that pressure, this pressure P, will be equalized by this liquid pressure, which is mercury. Okay, so when the pressure exerted by this mercury will be equal to the atmospheric pressure, this will stop going further down. Okay, and that is exactly equals to the atmospheric pressure. So we can calculate with the height of this, we can calculate the pressure. Okay, and this height will come out. You can measure this height with the help of scale. So it comes out to be 760 millimeter. Now, what we are going to do? We are going to measure the pressure. So, this is the container and this is the tube that we have. Okay. So, let's say these are the mercury oxide. This is also mercury. So we have considered this point and this point. This point is A and this point is B. Now, according to Pascal's law, we can say that on the same horizontal level, the pressure exerted by the liquid is same. Inside the liquid is same. Okay, that is the Pascal's law. So PA is equals to P atmospheric. So PB should also be P atmospheric. So PA is equals to PB is equals to P atmospheric. Now we know that PB is nothing but, let's say this height is H. Okay, this height is H and PB is the pressure exerted by this mercury. Okay, which is given by rho G H. Rho of Hg, G into H of Hg, height of Hg column. Rho, which is the density, we know it is 13.6 10 raised to the power 3 kilogram per meter cube into 10 into height of mercury column. And this all equals to P atmospheric. Height of Hg column we also know. Okay, it is 760 and by the calculation of this, it will come out to be 0.760 meter or 760 mm. Okay. If you put the value first by measuring this, then the pressure, atmospheric pressure that you will have is 1.01 into 10 raised to the power 5 Newton per meter square. Now, any one of you can wonder this, why we are using only mercury, why we are not using water. So without atmospheric pressure, your body will be like this. See the video. See, suppose this is your body, and if there is no air, then what will happen to you? We have sucking the air, so this will happen to your body. Okay, got it? So that is why the astronaut wear that particular specific type of suit, because there is no air outside. Got it? So there is a very heavy pressure which is trying to crumble the body inside. Got it? Now, why atmospheric pressure at a height of about 6 km decreases to nearly half its value at the sea level, though the height of the atmosphere is more than 100 km? Why it is so? 6 km पे ही half हो जाता है, and the height of atmosphere is spread to be 100 km. So why it is happening? It is because of this. See the video. At ground level, these are the number of molecules. Let's say these are the number of molecules of atmosphere. So at ground level, the intensity of gravitational field G is high, and as you move up, the gravity will decrease. So at high altitude, you will have less number of molecules. So that is why the pressure will decrease at half, about 6 km, because more density in this area. Although it is spread to 100 km, but on 100 km, what you will have? You will have nothing like this. Got it? So that is why as the height increases, the atmospheric pressure also decreases. Got it? Now, for example, so this is the question that I'm asking you, that in a standard barometer developed by Torricelli, why mercury is used in place of water? We can use water. We have the chances to have the water. Okay. So why we are using the mercury? So it is because firstly we know that atmospheric pressure is equals to 1.01 10 raised to the power 5 Newton per meter square, or you can also say it is Pascal. Okay, because 1 Newton per meter square is equals to 1 Pascal. Got it? Now, in this question, density of mercury is given to you is 13.6, 10 raised to the power 3 kilogram per meter cube. And density of water is given to you as 1000 kilogram per meter cube. Okay. Now, if you talk about that, what should be the height of column? Height of the water column will be, because height of the water height of the mercury column we know it is 760 mm or 76 centimeter. Now we are going to calculate that how much the water will rise on that tube. Okay, so P atmospheric is equals to rho gh, rho of water. We have replaced the mercury with water. So rho of water means density of water into gravitational acceleration multiply with the height of the water column. Same as we have a height in mercury column, so we have some height in water column also. So we are going to calculate that how much is the height for water column. So if you do the calculation, it will result in 10.29 meter. Look, 10 meter, about 10.3 meter long. So look, see how long is the pipe will be if you construct a barometer with the help of this water. Okay, so this is not feasible for us to have that much amount of height. Okay, in mercury if you will compare, it is just for mercury it is 0.76 meter, and for water it comes out to be 10.29 meter. Look, what is the difference? How big is the pipe should be? So you have to take a very long pipe to measure the atmospheric pressure, which is not feasible for us, and it is also not economical. Okay, if you calculate the height of mercury column, it will be 0.757 or 760 approximately. Okay, so it is not feasible to use water because it requires large tube of length 10.29 meter. So for each time you need to measure the atmospheric pressure, you need to put that 10.2 meter long pipe on that container. And who are going to measure it? You know? So it is feasible for us to use mercury as the liquid for measuring atmospheric pressure. Now, just a second, few more information I want to give you. In the early centuries, Aristotle is the philosopher. Aristotle believed that nature abhor the existence of nature. Sorry, vacuum. Aristotle was thinking that there is no such kind of vacuum can exist because nature defend itself to being vacuum. So if there is anything is vacuum, so the matter will immediately fill, the surrounding matter will immediately fill this void. So there is no existence of the vacuum. It is the statement of Aristotle, which is a great philosopher. But what happened? And this idea, this thought was to be believed over a 2000 years, and that is not questionable. Now, until the necessity is raised to question this, so what will happen when we are constructing the head pump? So what will happen in the downstairs, in the earth surface, we dig a hole and we set up a hand pump. So what will happen when we are pushing the water up? It will only rises to 10.29 meter. and above that it will not rising. So what will the people think? That the force that we are exerting is not sufficient to pull the water up. Okay, but this is not the case. Okay, because if there is nothing inside, only the water is, and if there is nothing inside, then who is exerting the force? So Galileo Galilei was the first to believe that there is a kind of mysterious force that exerting that has been exerting on water, so that water is not coming up to the 10.29 meter. Now the young scholar of Galileo Galilei, who is named is Torricelli, okay, came into the picture, and he has developed a setter of water. Here is the water, and there is a tube which is also filled with water. He put this tube inside this liquid and opened the cap, so that the liquid inside this tube will drop to a certain height. And when this height is to be measured, this will exactly equals to 10.29 meter. Now, what is this? This is vacuum. So it is the direct controversy to the Aristotle idea. Okay. And this idea somehow was not acceptable by the Galileo Galilei itself. Okay. But Torricelli was very young scholar. So he has a curiosity that how can I be wrong? Okay. So he used that concept that this pressure, this water pressure, is balanced by the atmospheric pressure surrounded by this glass tube. In the surrounding of this glass tube, the atmosphere exerts a pressure on it, the surface, and that will be balanced by this weight which is inside the container, which is inside this glass tube. So this weight is balanced by this atmospheric pressure. Then he used mercury instead of this water and developed the barometer. But this barometer was very useful device up to 2007, because after 2007 it was being stopped in Europe. And why it is so? Because of because of toxicity of mercury. Mercury is a toxic compound. So because of that, we have stopped using mercury as a liquid inside the barometer. Got it? Now, this is the idea I want to give you. Now, gauge pressure. So what is a gauge pressure? In everyday life, when you will become an engineer or a technician or whatever, the device that we use to measure the pressure, they will actually measure the gauge pressure. Okay, not the net pressure. Got it? And what is that? No. Pressure which is measured with respect to the atmospheric pressure, which means you would consider atmospheric pressure is there, but you will consider it to be a reference line. And then above that, what is the pressure is termed as gauge pressure. So gauge pressure is nothing but, like, this is a gas. This gas is exerting the pressure on this liquid. This gas is exerting the pressure on this liquid, and there is an atmospheric pressure on this side of the liquid. But these are at the same level. This is the atmospheric pressure. Rho is the density of this liquid. This is the height difference. This is the height difference. Okay. Now, this is termed as the open tube manometer. It is also a device to measure the gauge pressure. Okay. So what will happen? We can see that at this point, let's say this point is A, This point is B. So we can say that pressure at point A is equals to pressure at point B. Now pressure at point A is exerted by the gas. So we can say that pressure of gas. Pressure at B is exerted by this liquid and the atmosphere. We can say that it is P at atmosphere plus rho G H. And that is what written in this equation. So here, if I get this difference, P gas minus P atmospheric, so this excess pressure is termed as this pressure. Let's say this is Pg. So this Pg is equals to rho Gh. This Pg is nothing but the gauge pressure. Somehow we have placed that P atmospheric is 0. Now, so it is P gas minus P atmospheric, which is equals to rho Gh. Now, P gauge is equals to rho Gh. So for that, with the reference of gauge pressure, we have assumed the atmospheric pressure to be 0. Now, I hope you are getting this, what I'm teaching you. If you have any kind of doubt, you can ask. Okay. Now, this is the diagram I have given you. And here's some data in this. This is the open tube manometer. The liquid is filled up to point A. And here's the gas, which is exerting pressure at this point. This difference of height is given you as 0.120 meter. Okay. And this liquid is of mercury. Mercury has a density of 13.6 kilogram per meter cube. Okay. So we have to calculate the pressure of gas in the given diagram. We are going to use this formula we have seen in the earlier slide. P goes is nothing but P gas minus P atmospheric is equals to rho Gh. Now, try to solve this question. I have given you 2 minutes. Okay. So Shiva, try to solve this question. You have 2 minutes to solve this question. Or get the idea like how to solve this types of question. Okay. All the data is given to you. The difference in height is given to you. The density of mercury is given to you. Okay. All you need to do, you need to apply the Pascal's law at the same level and do the calculation. Now, so when we go down, pressure increased. When we move up, pressure decreased. This is the concept because pressure depend on the depth. So as the depth increases, the pressure increase. As the depth decrease, which means we are moving up, so pressure will decrease. So here at this point C, we can apply the Pascal's law. PC is equals to nothing but PB. PC is purely P of gas. PB is nothing but the pressure exerted by this liquid and the atmospheric pressure. So P atmospheric plus rho of this liquid G into height of this liquid, which is given to us. Okay. So if in the question, if it is asking that what is the gauge pressure, so you do not need to consider this atmospheric pressure. Okay. So P atmospheric minus P gas is equals to rho Gh. Got it? All of the thing is given to you. So 13.6 10 raised to the power 3 is the density of mercury. G is 10. H you have taken 0.120, which is given in the question. Plus P atmospheric. P atmospheric is 1.01. 10 raised to the power 5 Pascal. You add up all of this. So you will have pressure of the gas as 1.17. 10 raised to the power 5 Pascal. Or if in this question, if I ask you what is the gauge pressure? Gauge pressure. So gauge pressure is nothing but Gauge pressure is nothing but you have to assume the atmospheric pressure to be zero. So only this will result in the gauge pressure. So gauge pressure is nothing but P actual minus P atmospheric. So P atmospheric you have to minus out. This is the actual pressure you have 1.17 raised to the power 5. If you minus the value of atmospheric pressure, so it will result in 0.16 10 raised to the power 5 Pascal. Okay, this is P goes. Got it? I hope you are clear with this question. Any kind you have, you can ask. Any kind of doubt you have. Okay. Now, we have seen the fluid which is in rest, and we have calculated the pressure variation with depth. Okay. But in this scenario, what we are going to see, we are going to see that what if we accelerate the vessel which have the liquid, then what is the effect on the pressure inside the liquid? So that is the calculation we are going to do. So here we have two types of acceleration. Firstly, we will accelerate the vessel in vertical direction, and then we will accelerate the vessel in horizontal direction. Okay, and we will see what is the variation in pressure in the liquid. So for that first case, we have considered the container having vertical acceleration. This is the container, and it is accelerating with a pressure was with an acceleration a, let's say. Okay, so what we have considered, it is filled with, let's say, some kind of liquid. Okay, got it? And in this, inside this liquid, we have considered a fluid element. This is the fluid element we have. Okay, got it? Now, in this fluid element, there is a pressure P1 which is acting on this surface. Let's say this surface is A and this surface is B. The height of this cylinder is H. Okay, so pressure at A will be PA, pressure of B will be PB, plus the weight of this object we have considered. Okay, so if the fluid is at rest, we can say that PA is equals to PB plus the liquid inside that, which is equals to rho GH. है ना? PA is equals to PB plus rho GH. If this height is not too large, we can consider it. Rho GH, how it come? Because the weight inside the liquid is mg. Let's see. And we put this here, mg. PA is equals to PB plus m. You can put, if the density of the liquid is given to you as rho, so you can put it at rho into height of this, the volume of this cylinder. If the surface area is A, height is A, H, so you can put it A into H into G. Got it? Now, this is the weight, but you have to calculate weight per unit area for the pressure. So you have to divide it with area. So you have to divide with area. Area and area will cancel out. So PA is equals to PB plus rho H G. Okay. So the difference of pressure in a static condition will be PA minus PB is rho H G. In the case of rest, so when the fluid is at rest. Now, when the fluid is accelerated, I will see it here, or let's say we will do it here. We have already discussed it, the variation of pressure with depth. Now, when the fluid, the container in which the fluid we have is accelerating with an acceleration A and in the vertical direction. So what we are going to do, we have considering this vessel only, the fluid element that we have considered. Now, moving upward, there is also the acceleration in this container. So applying, we have to apply the Newton's second law. Newton's second law. Because now this time, this vessel is also accelerating with acceleration A in upward direction. So what do we have? Let's say the force on this surface is Fa, force on this surface is Fb on surface B. So we can say that, and weight of the liquid is also there. We can say that F net is equals to mass of the vessel into acceleration of the vessel, ma. Okay, so we are applying this for only for this fluid element, so we have to consider the mass of only this fluid element. Yeah. Now net force is the Fa minus, why minus? Because these Fb and mg is acting opposite to the acceleration. So minus of Fb minus plus mg equals to mass into acceleration. Now Fa minus Fb minus mg equals to ma. Fa minus Fb is equals to, if you take this mg on this side, it will become m into g plus a. Now Fa and Fb you need to put in terms of pressure because we are going to calculate the pressure. Fa you can put it as pressure at A into area minus Fb is also pressure of B into area is equals to m into g plus A. Now Pa minus Pb is equals to m g plus A divided by A. A is the area here. Now Pa minus Pb is nothing but is equals to mass you can put in terms of density of the liquid and volume. Now we have this fluid element. The area is A, height is h, so volume is A into h. Volume of liquid element equals to area into height. Okay, so you need to put this mass in terms of volume and density. Density of the liquid is rho, volume is A into h into g plus A divided by area. Area and area will cancel out. So you can see here this Pa minus Pb, which is the difference in pressure, is equals to rho g plus A. Okay, sorry, rho into g plus A into h. So this acceleration is add up into this. So the vessel is moving up. The first case is moving up. Okay, so you need to add initially at rest. What you will have? You will have Pa minus Pb is rho gh. But when the liquid or the container is moving upward with an acceleration, now the pressure difference you have as rho into g plus A into h. A is the acceleration of the vessel. In this scenario, you will keep remember that in this case the container is moving up, so that is why it is g plus A. But what if the container is moving down? So if container is moving down. Okay, with an acceleration a. So PA minus PB will be PA minus PB is equals to rho G minus A into H. You can modify this value G minus A based on if this acceleration given is greater than this G. So you can put there at A minus G. Okay, got it? So I hope you got this concept. Any kind of doubt, Shiva? If you are having, then please ask. Okay. So this is the pressure variation when liquid inside the container is accelerating. Okay, with an acceleration A, and it is moving upward with A. So you need to put G plus A into H. Now, in the next case, we have container having horizontal acceleration. Okay. Now this container is horizontally accelerated with an acceleration A. The length of this cylinder we have considered L. Okay. And the base area is A here. Let's say this height of the liquid is H1, or let's say H2, and this height of the liquid is H1. So when you have a container filled with liquid, you accelerate it horizontally. So you will also do this experiment on your home. You take a glass, fill it with the water, and make it horizontally accelerated. So you will see that the surface of that glass will tilt. Okay, surface of that glass, the water at the surface will be tilted. Okay, it will go down on this face, which is accelerating in this direction, and the opposite face it will go up. Got it? And we are going to see the reason for that. Got it? Now, in this, we will consider this cylinder to be the same horizontal level. So at vertical level, there is no change in pressure because all the cylinder is lying on the same line. Okay? But on the horizontal level, the pressure would also be same. But here the vessel is accelerating. Got it? So we need to calculate that what is the difference between the pressure at this surface. Let's say this surface is A and this surface is B. So we are going to calculate the PA minus PB. Okay. We know that this fluid element that we have considered in the orange shape has mass M. So this mass M is accelerating in this direction. So we can apply the Newton's second law. Apply Newton second law. So Newton's second law says that net force is equals to mass into acceleration of the vessel. Okay. Now, okay, here you have PB and PA as the pressure. So if you consider this PA, this will at a height H1, let's say, and to calculate this PB, it is at height of H2. Okay. This line is below at this point at height H2, and this line is below at height H1. Okay. So PA at this level, if you calculate, it will become the force FA and FB. So FA, if you are going to calculate, it is nothing but pressure at A into area of A. Now pressure of A will be rho G H1, the difference in height H1, and FB, if you will calculate, it will result in rho B A into rho B into A. Sorry, rho नहीं ये है P, PB into A. Pressure at B. So we know that for a container having liquid at height h, and if you want to calculate the pressure at that point, so it is rho g into depth of the liquid. So here the depth is h2. So we will calculate it rho g h2 into a. Okay. Now according to Newton's second law, we put the value. Fb is in the direction of acceleration, so we can say that Fb minus Fa is equals to mass of the liquid into acceleration. Fb is nothing but rho g h2 into a minus Fa is nothing but rho g h1 into a is equals to mass into acceleration. Now from here h2 minus h1 divided by into rho g a is equals to mass into acceleration. Now again we would put the value of mass in terms of volume and density. So mass is nothing but mass is equals to rho into volume, and volume is nothing but area into the length. Here it is given as L. Okay. And let's say the tilt angle will be theta. Now we can do that h2 minus h1 is equals to into rho g a equals to mass, you can put at rho into area into length into acceleration a. Okay. This rho and this area will cancel out. So you will have as h2 minus h1 divided by L is equals to A upon G. Okay. So this is the relation you will have. This h2 minus h1 is L, and this h2 minus h1 by L will become, if you see, this height is the h2 minus h1 because this complete height is h1. This is h2. So this difference will become h2 minus h1. Okay. Got it? Now, you need to put this in the equation. So the tilt angle you will have tan theta is equals to A by, just a second, A by G, which is also equals to difference of height of the level of the liquid divided by the, so this is the formula you will have. Just give me a 10 second. Okay. Just a second. So sorry for the disturbance. So we can easily see here that for a liquid which is horizontally accelerated, there is a tilt in the liquid, and we can also say that the pressure is not It's not same. ठीक है, because we know that tan theta here will come as h2 minus h1 divided by L is equals to A upon G. Okay. In similar way, you can see if you multiply this GH2 with here and L with this, so it will become, if you put this H1 as 0, we have considered this H1 as 0, so put H1 is equals to 0. This will you have as H2 as H divided by L is equals to A upon G. So A here is nothing but Hg upon L. Okay. If you multiply both the side with rho, that will become rho Hg divided by L. If you if you see this rho Hg is nothing but the pressure at height H, at depth H. So it is pressure is equals to rho length of the liquid element that you have considered into acceleration of the vessel. You can clearly see the pressure is not constant. It has a value of rho L into A. Okay. So this is because of this acceleration. Got it? Okay. So this is it from my side. If you have any kind of doubt, you can ask. Otherwise, the lecture is being over. Thank you so much for being attentive. I hope you enjoy the session. Okay. So the lecture is being over. Thank you so much. Any kind of doubt you have, you can ask. Thank you so much, Shiva, for being attentive and being responsive also. Try to solve the question from this topic. Okay. Thank you so much.